Yo, Code Pilots! Welcome to part 1 of the Python OOP Masterclass, a journey into object-oriented programming. Today, we'll introduce classes, objects, and why OOP matters. Hit that like button, and let's start. Let's start with what OOP is. It's a programming paradigm where we organize code into objects, which are instances of classes. Think of a class as a blueprint, like a car design, and objects as the cars built from it. This approach makes code reusable, modular, and easier to manage, setting the stage for big projects. First, let's define a class. In Python, use the class keyword like class car. Inside, we can add attributes, data, and methods, functions. A simple attribute might be color equals red, and a method could be drive that prints a message. This is our first step into creating objects. To create an object, we instantiate the class with myCar equals car. This builds an instance based on the blueprint. We can access attributes with myCar.color or call methods with myCar drive. This shows how classes turn into real, usable objects in your code. Let's add a constructor with init. This special method runs when an object is created, letting us set initial attributes. For example, def init self-color. Self-color equals color lets us do myCar equals car. It's key for customizing objects right away. Now, let's use methods. Define a method like defDrive, self. Print the self-color car is driving. The self parameter refers to the instance, linking attributes and methods. Call it with myCar drive, and you'll see the color in action. Try it to see the output. Let's explore attributes more. We can have instance attributes set in init, like self.speed equals 0, or class attributes shared by all instances, like car.brand equals Toyota. Access them with mycar.speed or car.brand to understand their scope in a class. Time for a practical example. Let's build a dog class with init, self, name, breed, and a method bark, self. Create my dog equals dog max, golden, and call my dog bark. This real-world object shows how classes model entities with behavior. Let's test our classes. Run my car drive and my dog bark to see the outputs. Change my car.color to green and call drive again. This hands-on practice helps you see how objects behave and how to tweak them. Classes are the foundation of OOP. They let you group related data and functions, making code cleaner than using standalone functions. This modularity is why OOP is used in games, apps, and more. Start thinking of objects as your building blocks. Let's think about next steps. We'll dive into inheritance and encapsulation soon, building on these basics. Practice creating your own class, like a book, to get comfortable, experiment, and have fun. That's a wrap for part 1. Code Pilots, you've started your OOP journey. Like this, subscribe, and share your class ideas below. See you in part 2. Keep coding. Yo, Code Pilots! Welcome to part 2 of the Python OOP Masterclass. Last time, we started with classes, and now we'll master constructors and methods. Hit that like button, and let's dive in. Let's recap and focus on constructors. The init method is a special constructor that runs when an object is created. It lets us initialize attributes, like setting a car's color or model, making each object unique right from the start. Let's explore this further. Let's create a car class with a constructor. Use def init self color model to set self color and self model. This allows us to instantiate with my car equals car red Toyota, giving us control over initial values for each instance. Now let's add a method to the car class. Define def describe to print the car's details, like print f self color, f self model car. Methods are functions inside a class that operate on the object's data. Call it with myCarDescribe to see it work. Let's make the method interactive. Add def change color, self new color to update self.color and print a confirmation message like printf color change to self color. Test it by calling myCarChangeColor blue and observe the change. Time for a practical example with a student class. Use init self name grade to set initial attributes like self name and self grade. Then add def study to print a message like print f self name is studying. Create my student equals student Ali 10. Let's enhance the student class with a method. Add def update grade. Call it with myStudent.UpdateGrade11 and check the output to see the validation in action. Now, let's add another method. Define def getInfo to return a formatted string like return f self name grade, etc. Call print myStudentGetInfo to display the student's details in a clean format. Let's test edge cases. Modify update grade to reject invalid inputs like negative grades with an if statement. Try myStudent.UpdateGrade-1 and see how the method handles it, ensuring data integrity. Methods can call each other for efficiency. Add def promote to increment self grade by 1 and call update grade if the new grade is valid. Use myStudent.promote to see how methods collaborate within the class. Let's add flexibility with a parameterized method. Define def greet self message to print f self name says. Now call it with myStudent.greet hello to see how it adapts to different inputs. That's a wrap for part 2. Code pilots, you've mastered constructors and methods. Like this, subscribe, and experiment with your own methods. See you in part 3. Keep coding. Yo, code pilots. Welcome to part 3 of the Python OOP Masterclass. We've built a foundation with classes and methods, and now we're diving into properties and practical coding. This will be detailed, so hit that like button and let's get started. Let's start by understanding properties in Python. Properties are a way to control attribute access using decorators like @property. They let us add logic, such as validation or computation, before getting or setting a value, acting as a gatekeeper for your object's data. This is different from direct attribute access, and we'll explore it step by step with examples to make it clear. To begin, let's create a car class. Define it with def initSelfSpeed to set an initial speed attribute. Then use @property with def speed self to return self_speed, using the underscore to indicate it's protected. Instantiate it with myCar equals car 100. Let's set this up and move to the next step. Now let's test this setup. Create myCar equals car 100 and run print myCar speed to see the initial speed. This shows how the @property decorator lets us access speed like an attribute. Take a moment to observe the output, and let's discuss why this is useful before adding more. Next, let's add a setter. Use @speed.setter with def_speed self value to check if value is greater than 0 before assigning it to self_speed. This prevents invalid speeds. Update the class with this setter. Let's add it and prepare to test it. Let's test the setter with myCar equals car 100. Try myCar.speed equals 120. To increase speed, then myCar.speed equals -10 to test the validation. Run print myCar.speed after each to see the results. This shows how the setter protects the attribute. Take time to understand the output. Now, let's add a deleter. Use @speed.deleter with defspeed.resetSelf._speed to 0. Add this to the car class. Let's include it and move to testing. Test the deleter. Create myCar equals car with 100. Set myCar.speed equals 150. Then use del myCar.speed and check with print myCar.speed. This demonstrates the full life cycle of a property. Pause here to see how it resets and why it's helpful. Let's move to a bank account class. Start with def__init : self balance to set self._balance and add @property with def balance self to get it. Create myAccount equals bank account with 1000. Let's set this up and test it next. Test the bank account setup. Run print myAccount balance to confirm the initial balance of 1000. This shows the getter in action. Take a moment to explore the output and get comfortable with this structure. Add a setter for balance. Use @balance.setter with def balance self amount to update self_balance if amount equals 0. Add this to the class. Let's include it and prepare to test. Test the balance setter with myAccount equals bank account 1000. Try myAccount.balance equals 1500 to deposit. Then myAccount.balance equals -500 to test validation. Check with print myAccount.balance. Discuss how this prevents negative balances. Let's add a withdrawal method. Define def withdraw self amount to subtract from self balance if amount is 0 and funds are sufficient. Add this. Let's include it and test it next. Test the withdraw method with myAccount equals bank account 1000. Run myAccount withdraw 300 and check print myAccount balance. This shows the method working with the property. Take time to see the new balance. Add error handling to withdraw. Modify it to raise a value error if amount is negative or exceeds balance. Update the class. Let's add this and test it. Test the error handling. With myAccount equals bank account 700, try myAccount withdraw 2000 and observe the value error. This protects the account. Discuss the error and its importance. Let's create a game character class. Use def init self health for self_health and add @property with def health to get it. Create myChar equals game character 100. Set this up and test next. Test the game character setup. Run print myChar health to see the initial health. This establishes the base. Take a moment to get familiar with it. Add a setter for health. Use @health_setter with def health self value to set self_health if 0 equals value equals 100. add this, let's include it and test. Test the health setter. With my char equals game character 100. Try my char. Health equals 80. Then my char health equals 150. Check with print add a take damage method. Define def take damage self damage to reduce self_health if the result is non-negative. Add this. Let's include it and test. Test take damage. With my char equals game character 100. Set my char health equals 90. Then my char take damage 40. And check print my char health. Discuss the result. That's a wrap for part 3, Code Pilots. You've mastered properties in practical coding with thorough testing. Like this, subscribe, and practice these concepts. See you in part 4. Keep coding. Yo, Code Pilots. Welcome to part 4 of the Python OOP Masterclass. We've covered properties, and now we're diving deep into inheritance. This will be detailed, so hit that like button and let's get started. Let's begin with what inheritance is. Inheritance is a core concept in OOP where a child class can inherit attributes and methods from a parent class. Think of it like a family tree. A car can inherit from a vehicle class. Reusing code and building on it. This reduces redundancy and sets up a hierarchy, and we'll explore this with car examples. First, let's create a vehicle parent class. Define it with def init self speed to set self.speed, and add a method def move to print vehicle is moving. This will be the base class for our car-related examples. Let's set it up and move forward. Let's test the vehicle class. Create my vehicle equals vehicle 60 and run my vehicle move to see the output. This gives us a starting point. Take a moment to observe the result and understand the parent class's role. Now let's create a car child class that inherits from vehicle. Use class car vehicle and add def init self speed brand to set self brand while calling the parent's init with super init speed. This links the child to the parent. Let's add it and test next. Test the car inheritance. Create my car equals car 100 Toyota. Run my car move to use the inherited method and print my car speed to check the inherited attribute. Take time to see how the child class builds on the parent. Discuss the output. Let's add a specific method to car. Define def honk self to print beep beep from self brand. This adds unique behavior to the child class. Let's include it and prepare to test. Test the honk method. With my car equals car 100 Toyota. Run mycar.honk to hear the car's sound. This shows how the child can extend the parent. Pause to explore this new feature. Let's create another child class, sports car, inheriting from car. Use class sports car car. With def init self speed brand top speed to set self.topspeed, calling super init speed brand. This creates a multi-level inheritance. Let's add it. Test the sports car class. Create my sports car equals sports car 200 Ferrari 300 and run mysportscar.move for the inherited move. Print mysportscar.speed for the car speed and print mysportscar.topspeed for the new attribute. Take time to see the hierarchy. Let's override the move method in sports car. Define def move to print sports car print is racing at self speed kilometers per hour. Update the class. Let's include it and test next. Test the overridden move in sports car. With my sports car equals sports car 200, Ferrari 300. Run mysportscar.move to see the racing message. This shows how a grandchild can customize behavior. Discuss the output. Let's add a practical example with a garage class. Use def in itself to hold a list of vehicles and def add vehicle to add any vehicle object. Add some car and sports car instances. Let's set this up. Test the garage class. Create garage equals garage. Add my car and my sports car with garage.addVehicle, my car, and garage.addVehicle, my sports car. Then print the list. This shows inheritance in a real-world context. Take time to explore. Let's enhance garage with a display all method. Define it to loop through vehicles and call move on each. Update the class. Let's add it and test. Test the display all method. Run garage display all to see all vehicles move. This demonstrates how inheritance allows a uniform interface. Pause to analyze the result. Let's add a speed check to display all. Modify it to print only vehicles with speed greater than 100. Update and test. Discuss how inheritance supports this filtering. That's a wrap for Part 4. Code pilots, you've mastered inheritance with car examples. Like this, subscribe, and try your own inheritance trees. See you in Part 5. Keep coding. Yo, code pilots. Welcome to Part 5 of the Python OOP Masterclass. We've mastered inheritance, and now we're exploring polymorphism. This will be a deep dive with lots of explanations. So hit that like button, and let's get going. Let's talk about what polymorphism is and why it's exciting. Polymorphism means many forms. It lets objects of different classes be treated as instances of a common parent class, even if they behave differently. Imagine a garage where all vehicles, cars, trucks, can move, but each does it its own way. This flexibility is powerful because it lets us write code that works with any child class without knowing its type ahead of time. Today, we'll see how this works with our car examples. So let's think about why this could make our programs more adaptable. To start, let's recall our vehicle class from last time, which has a move method. We're going to use it as the parent class again. The idea here is to let different types of vehicles inherit from it, but each can redefine move to suit itself. This is the foundation of polymorphism, and it's worth taking a moment to appreciate how it sets up a shared interface. Let's set the stage by looking at that class again. Now let's think about why we want to use polymorphism. Imagine you're building a racing game where different cars need to move differently. A regular car cruises. A sports car races. Instead of writing separate code for each, polymorphism lets us use one function to handle all types. This saves time and makes the code easier to maintain. So let's create a car class again, inheriting from vehicle, and we'll add a custom move. Let's plan this out before jumping in. Let's build the car class. We'll use class car vehicle with def init self speed brand to set self brand and call super init speed. Then let's override move to print something like car self brand is cruising at self speed kilometers per hour. The goal here is to show how the child can change the parent's behavior. Let's add this and take a breath to see what we've done. Before we test, let's discuss what we're achieving. By overriding move, we're giving car its own identity, while still fitting into the vehicle family. This is the heart of polymorphism. Different forms under one roof. Now let's test it. Create my car equals car 100 Toyota and run mycar.move to see the cruising message. Take a moment to watch the output and think about how this differs from the parent. Let's add another vehicle type to see polymorphism in action. We'll create a sports car class, also inheriting from vehicle, with def, init, self, speed, brand, top speed, and a move method that prints sports self-brand is racing at self-speed kilometers per hour. The reason we're doing this is to show how multiple classes can offer different behaviors under the same method name. Let's set this up. Let's test the sports car too. Create my sports car equals sports car 200 Ferrari 300 and run my sports car.move to see the racing message. This reinforces our point. Both car and sports car use move, but each does it differently. Pause here to let that sink in and think about the flexibility this gives us. Now let's talk about why a function can treat these differently. We'll create a move vehicle function that takes any vehicle object and calls move. The beauty here is that it works for any child class without us needing to check its type, saving us from writing repetitive code. Let's add this function and plan how we'll test it. Let's test move vehicle. Define def move vehicle, vehicle.move, then call it with move vehicle, my car, and move vehicle, my sports car. Watch the different outputs. This is polymorphism at work. The function doesn't care which vehicle it gets. It just triggers the right behavior. Take time to discuss why this is a game changer for coding. Let's apply this to a practical example. We'll use a racetrack class with a method startRace that takes a list of vehicle objects and calls move on each. This mimics a real scenario where different cars race in their own style. Let's set this up and think about how it leverages polymorphism. Test the racetrack. Create racetrack equals racetrack. Add my car and my sports car to a list. And run racetrack.startRace with my car and my sports car. See how each vehicle moves differently. This shows polymorphism in a race context. Pause to explore the result. Let's enhance startRace to declare a winner based on speed. Modify it to find the fastest vehicle and print the result. This adds a practical twist. Let's update and test it to see who wins. Test the winner feature. Run the race again and check the output to see the fastest vehicle. This wraps up how polymorphism, combined with inheritance, powers dynamic applications. Take a moment to reflect on this. That's a wrap for Part 5, Code Pilots. You've mastered polymorphism with car examples. Like this, subscribe and experiment with your own polymorphic designs. See you in Part 6. Keep coding. Yo, Code Pilots. Welcome to Part 6 of the Python OOP Masterclass. We've covered polymorphism, and now we're diving into abstraction. This'll be a detailed journey with lots of explanations, so hit that like button and let's get started. Let's unpack what abstraction is and why it's a big deal. Abstraction is all about hiding complex details and showing only the essentials to the user. Think of a car. When you drive, you don't need to know how the engine works. You just press the pedal. In coding, this means creating classes that expose simple interfaces while keeping the messy stuff hidden. It makes code easier to use and maintain. And today, we'll explore this with our car theme. Let's talk about why to get started. Let's think about why abstraction matters. Imagine you're building a system with lots of vehicle types: cars, trucks, buses. Without abstraction, users might accidentally mess with internal engine details, causing errors. Abstraction lets us define what users can do, like start or stop, without exposing how it's done. We'll use the vehicle class as a base and add abstraction tools. Let's take a moment to appreciate how this simplifies things before we begin. In Python, we can use the ABC module for abstraction, which stands for Abstract Base Classes. This lets us create a blueprint that forces child classes to implement certain methods. The goal here is to ensure every vehicle has a start engine method, but we won't define how. It's up to the child. Let's import ABC, create an ABC class called vehicle, and add an abstract start engine method. Let's plan this out carefully. Let's build the abstract vehicle class. Use from ABC import ABC abstract method, then class vehicle ABC with @abstract method over def start engine self pass. This tells Python this is a blueprint. Child classes must fill in the details. The reason we're doing this is to enforce a standard across all vehicles. Let's add it and discuss what it means. Before moving on, let's talk about the power here. By making start engine abstract, we're saying every vehicle must have this ability, but the implementation can vary. This protects our code from incomplete designs and makes it more robust. Now, let's test this setup by trying to create a vehicle instance. Spoiler, it won't work. Let's see the error and understand why. Since we can't instantiate vehicle, let's create a car class that inherits from it. Use class car vehicle and implement def start engine self to print car engine starting with a roar. The purpose is to show how a child fulfills the abstract requirement. Let's add this and prepare to test. Let's test the car class. Create myCar equals car and run mycar.startEngine to see the message. This works because car provided the missing piece. Take a moment to see the output and think about how abstraction guides us. Let's also discuss why this prevents someone from using an unfinished class. Let's add a sports car class to see more variety. Use class sports car vehicle with def start engine to print sports car engine revving at high RPM. The idea is to show different implementations while sticking to the abstract rule. Let's set this up. Test the sports car class. Create mySportsCar equals sports car and run mySportsCar.startEngine to see the revving message. This highlights polymorphism within abstraction. Pause to reflect on how both classes meet the same standard differently. Now let's think about a practical use. We'll create a garage class with a method startAllVehicles that takes a list of vehicle objects and calls startEngine on each. This leverages abstraction to manage any vehicle type. Let's plan this out and add it. Test the garage class. Create garage equals garage, add myCar and mySportsCar, and run garage.startAllVehicles, myCar, mySportsCar. Watch the different start messages. This shows abstraction in action. Let's discuss why this makes the garage code flexible. Let's enhance startAllVehicles to check if each vehicle starts successfully. Add a simple condition, like printing a confirmation. Update it. Let's test and talk about how abstraction helps us add features without breaking the system. Test the enhanced startAllVehicles. Run it again and see the confirmations. This wraps up how abstraction simplifies complex systems. Take a moment to appreciate the elegance of hiding details. That's a wrap for part 6. code pilots. You've mastered abstraction with car examples. Like this, subscribe and try applying abstraction in your projects. See you in part 7. Keep coding. Yo, code pilots. Welcome to part 7 of the Python OOP Masterclass. We've covered abstraction, and now we're diving into encapsulation. This will be a thorough session with plenty of explanations, so hit that like button and let's get going. Let's start by understanding what encapsulation is and why it's a game changer. Encapsulation is about bundling data and the methods that operate on that data into a single unit, while also controlling access to it. Think of a car's dashboard. You can turn the key, but you can't directly mess with the engine's wiring. In coding, this protects the internal state of an object from outside interference, making our programs safer and more reliable. Hey, have you ever wondered why some apps crash when you tweak the wrong setting? That's where encapsulation comes in to save the day. Let's talk about why this matters for keeping things organized. So why do we need encapsulation? Imagine you're working on a team and someone accidentally changes a car's speed to a negative number, breaking the logic. Encapsulation lets us hide that speed value and only allow controlled changes through methods. This reduces errors and keeps the code's integrity intact. Oh, and here's a practical tip. In real projects, this also helps when you need to debug. Knowing data changes only happen through specific methods makes tracking issues way easier. We'll use our vehicle class to explore this. Let's take a moment to think about how this could save us from chaos. In Python, we achieve encapsulation using naming conventions like single or double underscores. A single underscore, for example, underscore speed, suggests it's protected, while a double underscore, example, underscore speed, makes it private with name mangling. The goal here is to control access, not just hide it. Hey, did you know this is super useful when you're sharing code with others? It sets clear boundaries. Let's create a vehicle class with a protected speed and a method to modify it. Let's plan this out with care. Let's build the vehicle class. Use class vehicle with def init self speed to set self underscore speed and add def set speed self speed to check if speed equals 0 before updating. The reason we're doing this is to ensure the speed stays valid. Oh, and a quick tip. Always add these checks in real code to avoid sneaky bugs. Let's add it and discuss how this protects the data. Before testing, let's talk about what we've gained. By using speed and a setter, we're telling other parts of the code not to touch the speed directly, only through our method. This is encapsulation in action, giving us control. Hey, in a real project, this could prevent a teammate from accidentally crashing your app. Pretty cool, right? Now, let's test it. Create myVehicle equals vehicle 60 and try myVehicle.setSpeed80 to see it work. Then myVehicle.setSpeed -10 to catch the validation. Let's watch the result. Let's add a car class to see encapsulation in a child. Use class car vehicle with def initialize speed brand, calling super.initialize speed and setting self brand. Add a private fuel level with a method def add fuel self amount to update it if amount is 0. The purpose is to show layered protection. Oh, and here's a practical note. Using private variables like fuel level is great when you want to hide sensitive data, like a game's health points. Test the car class. Create myCar equals car 100 Toyota. Run myCar set speed 120 for the inherited method, and my car, add fuel 50 to check the fuel. Then try my car, add fuel -5 to see the limit. This shows how encapsulation works across inheritance. Pause to explore the outputs. Hey, notice how this keeps the car's fuel from going negative? That's encapsulation protecting us. Let's discuss why this is powerful. With _fuel level, even if someone knows the name, Python's name mangling, e.g. /car_fuel level, makes it hard to access directly. This adds a layer of security. Let's try accessing _grand and _fuel level directly to see what happens. Oh, and a tip. In real code, always document these private attributes to avoid confusion for your team. Before we move on, let's think about a practical angle. Encapsulation isn't just about hiding, it's about controlling how data evolves. For example, you could add a method to check fuel before starting the car, ensuring it won't stall. That's a real-world use case. Let's test accessing those attributes and talk about the results. That's it for the core concepts. We've seen how encapsulation bundles and protects data with our car examples. Hey, next time you're coding, try adding a setter with validation. It'll save you from headaches. Let's wrap up by testing those direct accesses. That's a wrap for Part 7, Code Pilots. You've mastered encapsulation with car examples. Like this, subscribe, and practice protecting your code. See you in Part 8. Keep coding. Yo, Code Pilots. Welcome to Part 8 of the Python OOP Masterclass. We've covered encapsulation, and now we're exploring composition. This will be detailed, so hit that like button and let's dive in. Let's start with what composition is. Composition is a way to build complex objects by combining simpler ones, like assembling a car from an engine and wheels. Unlike inheritance, it focuses on has-a relationships rather than is-a. This makes code more flexible and reusable. It helps avoid deep inheritance trees. Let's see why this could simplify our projects. Why use composition? It lets us swap parts easily. If a car needs a better engine, we just replace it without rewriting the whole class. This is handy in real-world scenarios like modular design. We'll use a car with an engine to explore this. Let's think about how this differs from inheritance. Let's create an engine class first. Use class engine with def init self power to set self power and def state self to print engine starting with self.power HP. The def init syntax here initializes the object with a power value. Let's include it. Now let's build a car class using composition. Use class car with def _init self brand engine to set self brand and self engine equals engine. Add def start self to call self engine start. The self engine assignment composes the car with an engine object. Let's add this. Let's consider the benefit. Composition lets us change the engine type without altering car. A practical edge over inheritance. We can test this later with different engines. Let's move forward with the concept. Let's add a wheel class. Use class wheel with def init self size to set self size and def rotate self to print wheel rotating at self size inches. The def init syntax sets up the wheel size. Let's add it. Update car to use composition with wheels. Add a list self.wheels equals wheel 16 for _init. The list comprehension here creates 4 wheels. The for underscore in range for loop iterates 4 times without using the variable. Let's set this up. Let's add a drive method to car. Use def drive with self to call self.wheels rotate. The dot notation self.wheels accesses the first wheel. Let's include it. Let's enhance engine with a stop method. Use def stop self to print engine stopped. This simple method adds more functionality. Let's add it. Update car to use stop. Add def stop to call self-engine.stop. The dot notation self-engine.stop accesses the composed objects method. Let's include it. Let's reflect on the flexibility. Composition shines when you need to test parts separately or swap them, like changing an engine. That's a wrap for Part 8, Code Pilots. You've mastered composition with car examples. Like this, subscribe, and try building with composition. See you in Part 9. Keep coding. Yo, Code Pilots! Welcome to Part 9 of the Python OOP Masterclass. So hit that like button and let's dive in. Let's start with what solid principles are. Solid is a set of 5 design guidelines: single responsibility, open-closed, Liskov substitution, interface segregation, and dependency inversion that help write better, maintainable code. They build on what we've learned, like encapsulation and composition. Let's see why these principles can make our car code more robust. Why use solid? These principles prevent common issues like tight coupling or hard-to-extend code. For example, a car system should be easy to update without breaking everything. We'll apply them step by step with our car example. Let's think about how they fit into our journey. Let's tackle single responsibility first. This means a class should have one job. Our car class might handle driving and fuel, which is too much. Let's create a fuel system class with def init self to set self.level equals 0 and def add fuel self amount to update if amount greater than 0. Note that def init initializes the object. Update car to use fuel system. Use self.fuelsystem equals fuel system in init and call self.fuelsystem.addFuelAmount in a new refuel method. The dot notation self.fuelsystem composes the system. Let's add this. Let's apply open-closed next. This says classes should be open for extension but closed for modification. Add a start method to fuel system to check self.level greater than 0. The if statement here handles the condition. This lets us extend behavior without changing existing code. For Liskov substitution, ensure a child class can replace a parent without issues. Create a sports fuel system inheriting from fuel system with a custom start. Use super.init to call the parent's init, a syntax for inheritance. Update car to accept any fuel system. Change init to self.fuelsystem equals fuel system. This uses a parameter for flexibility. Let's add this to support substitution. Let's move to interface segregation. This suggests small, specific interfaces. Define an iVehicle class with addAbstract method def drive self from ABC. The addAbstract method decorator marks it as abstract. Implement iVehicle in car with def drive self to print car is driving. The def here fulfills the interface. Let's include it. Finally, dependency inversion. This says high-level modules shouldn't depend on low-level ones directly. Use iVehicle in a race class with def start race self vehicle iVehicle. The type hint vehicle iVehicle specifies the dependency. That's a wrap for Part 9, Code Pilots. You've mastered solid principles with car examples. Like this, subscribe, and apply these in your code. See you in Part 10. Keep coding. Yo, Code Pilots! Welcome to Part 10 of the Python OOP Masterclass. We've mastered OOP concepts, and now it's time for a final project, a library management system. This will be detailed and exciting, so hit that like button and let's dive in. Let's set the scene for our project. We're moving away from cars to build a library management system using inheritance, polymorphism, abstraction, encapsulation, composition, and solid principles. Imagine a digital library where books are tracked, borrowed, and returned, with librarians managing it all. This project will showcase all we've learned, and I'll explain every step deeply: attributes, methods, public versus private, and why our design choices matter. Let's plan a system that's both functional and well-structured. First, let's define our base class with abstraction. We'll use from ABC, import ABC, abstract method. ABC is for abstract base classes, and @abstract method enforces method implementation. Create class item ABC with @abstract method def get info pass. The pass keyword is a placeholder, ensuring child classes define this method. This abstraction hides implementation details, like how each item's info is formatted, which is crucial for a scalable design. Let's create a book class inheriting from item. Use class book item. The parentheses show inheritance. Add def init, self, title, author, ISBN. Self underscore title equals title, self author equals author, self ISBN equals ISBN, the single underscore. Suggest protected attributes, a form of encapsulation. Implement def info, return F. Let's add composition with a library class. Use class library. With def init, self underscore items equals underscore. The list self items stores all items, again using underscore for protection. Add a public add item method. Def add item item append. This append method adds to the list, and this method's public nature allows external addition of items. A deliberate design choice for usability. Let's apply encapsulation with a private status. In book, add self underscore available equals true in init. The double underscore uses name mangling to hide this attribute, preventing direct changes. Add a public borrow method. Def borrow self, if self underscore available equals false, return true. The if checks availability, and return sends the result, showing controlled access, which is key for data integrity. Let's use polymorphism with a magazine class. Use class magazine item with def init self title issue. Self underscore title equals title. Self underscore issue equals issue. And override def get info self return F the title issue issue. This different implementation showcases polymorphism, letting each item type format its info uniquely. The override is a public method, intentional for consistency. Add abstraction with a borrowable interface. Use class borrowable ABC with @abstract method def borrow self pass and @abstract method def return item self pass. These abstract methods enforce borrowing logic. In book, implement def return item self underscore available equals true. The assignment updates the private state, fulfilling the interface. Let's apply solids single responsibility. Create a librarian class with def init self name. Self underscore name equals name. And def manage borrow self item return item borrow. This class handles borrowing, not item details, adhering to one responsibility. The dot notation item borrow calls the method, a public interface choice. Use dependency inversion with a library system class. Use class library system with def init, self-librarian. Self-librarian equals librarian. The parameter librarian injects the dependency. Add def process borrow self-item, return self-librarian manage borrow item. The type hint could be added, but we'll keep it simple, decoupling high level from low level. Let's explain the design. Attributes like underscore title are protected for internal use. Underscore available is private for safety. And public methods like getInfo provide access. Every choice, from abstract method to private attributes, supports maintainability. Let's appreciate the depth. That's a wrap for Part 10, Code Pilots. You've built a library system and mastered OOP. Like this, subscribe and tackle your own projects. See you in Part 11. Keep coding. Yo, Code Pilots! Welcome to Part 11 of the Python OOP Masterclass. We've reached the end of our OOP journey, and this is our final recap and send-off. This will be a heartfelt session, so hit that like button and let's wrap up together. Let's start with a big congratulations. You've come a long way, from understanding classes and objects to mastering inheritance, polymorphism, abstraction, encapsulation, composition, and solid principles. We built projects like the car simulation and library system, applying each concept step by step. This part is about reflecting on that journey, celebrating your growth, and looking ahead. I'll dive deep into what we've achieved and why it matters for your coding future. Let's take a moment to feel proud. Let's revisit inheritance. It let us create hierarchies, like vehicle to car, reusing code efficiently. The syntax, class child parent, was our foundation. And super, which calls the parent's method, helped manage initialization. This built a structure where child classes could extend behavior, a powerful tool for scalability that you can use in any project. Next, polymorphism gave us flexibility. Overriding methods like drive in different classes allowed varied behaviors under the same interface. The def keyword with a redefined method was key, enabling dynamic dispatch. This adaptability is what makes OOP dynamic, and it's something you can apply to customize software for different needs. Abstraction hid complexity with abstract base classes. Using from ABC import ABC, abstract method and @abstract method def method pass ensured a blueprint that child classes followed. The pass acted as a placeholder, enforcing structure without implementation, perfect for designing systems where details can evolve. Encapsulation protected data with access control. Attributes like self_private used double underscores for name mangling, while self_protected suggested caution. Methods like getters and setters, defined with DEF, controlled access, ensuring data integrity, a critical skill for secure coding. Composition built objects from parts. Solid principles tied it all together. Single responsibility kept classes focused. Open-closed allowed extension without change. Liskov substitution ensured substitutability. Interface segregation broke interfaces into small pieces. And dependency inversion decoupled dependencies. Now, let's look ahead. You're ready for advanced topics like design patterns, frameworks, or even game development with Pygame. Practice by building your own projects, maybe a school management system or a game. The skills you've gained, from super to solid, are your toolkit for the future. Before we go, a huge thank you. Your support, questions, and engagement made this journey amazing. This isn't goodbye, it's a see you later. Subscribe, check the playlist for review, and share your projects with me. You're now a code pilot ready to soar. That's a wrap for part 11. Code pilots, you've conquered OOP. Like this, subscribe, and keep coding. Until next time, take off.